What we're about to do here is some pretty cool, pretty powerful stuff. Specifically, we're going to find out what are the actual forces that need to exist in certain muscles and in certain joints in order to keep an arm in a static equilibrium position. Okay? These are the kind of questions that physical therapists have to think about all the time in order to keep people's bodies working in the most functional and stress-free ways. Okay? So if you guys could first go to the slide that says the 3 steps of analyzing static equilibrium. Okay? So as you know, I love doing very simple step processes to get to an answer. Stuff that you can apply to every single problem so that you always know where to start. Okay? So the first step is to draw a very clear free body diagram. Hopefully by this point in the course, you realize how important that is, because the free body diagrams just let you read off all the forces that let you solve the problem. Okay? 2, you want to pick your axis of rotation. This is very, very key. Technically, we could pick any axis of rotation, although there's a few caveats. In most cases, it makes the most sense to pick an axis of rotation that is actually fixed, right? That is actually the object, the point that something's going to rotate around, right? In the case of a joint, that's very, very obvious, all right? The other caveat when picking an axis of rotation is, you'll see why in a moment, but it's helpful to pick an axis of rotation that already has a force acting on it. And not to ruin the ending, but because torque is RF sine theta, if you pick a axis of rotation with a force already acting at that point, R is equal to 0, so that term in the torque equation disappears, and it makes the torque equation a little bit easier. All right? You'll see how that works out in the example we're about to do. 3, use your free body diagram to write out the 3 equilibrium conditions. Again, that's sum of forces in x equals 0, sum of forces in y equals 0, and sum of torques equals 0. Okay? And then lastly, the last step of almost every process that I share with you is solve for what you're looking for. Okay? And we are going to use this 3-step process on this problem that is in the next slide. It says equilibrium in the human body. Find the forces the elbow and the bicep must apply to the arm to keep it in static equilibrium. Okay? This is powerful stuff. You're going to be calculating something that the body naturally has to calculate in order to survive. Okay? So let's give it a shot. We have an arm, right, which I'm going to try to make as simple as possible. This is a hand. Oh my God, this is terrible. I don't even know. Damn, sorry. Okay, and so this is the elbow, right? Here is a bicep, right? Why, this doesn't look like a hand. Yeah, I guess that's a little bit better. All right, it's a little bit better, okay? And so this is the elbow right here, okay? And so you see there's a bone acting on it, right? And so there's actually going to be a force of that bone acting on the elbow. So I'm going to call that FE for elbow force. Okay? And you also have this, bicep muscle here, right? And that bicep muscle is applying a force to the arm very, very near to it. I'm going to call that force B for force bicep. Okay? Right? I'm bring this even a little bit farther down, right? So the bicep's pulling up on the arm, and that distance is very small between the two of them, right? That distance is 4 centimeters, which is going to be equal to 0.04 meters, okay? In addition to that, you also have the weight of the arm itself, right? I'm just going to call that W arm, right? And the mass of the arm is equal to 2.5 kilograms. Okay? And it also specifies that this distance here is 16 centimeters, which is 0.16 meters. Lastly, the person is holding a physics book. Okay? And so that book also has a mass, right? So it's going to be the weight of the book. And it tells us that this book weighs 4 kilograms. Okay? And so I think that's it, right? We have 4 forces: the force of the elbow, the force acting on the elbow, the force of the bicep pulling up the arm, which you can see from this, it's the only force going up, so that bicep's got a lot of work to do, right? The whole reason we're able to hold our arms in this position is because of this bicep. That's the only thing doing it, okay? You sever that bicep, your arm just is going to go limp, all right? You have the weight of the arm pulling down, and you have the weight of this book pulling down, okay? We have all our forces, so step 1 is done. We've already made an amazing free body diagram, right? Very clear. We know where everything is. The one thing that I didn't say is that this is acting 0.38 meters or 38 centimeters, 0.38 meters away from the axis of rotation from the elbow. Okay? Next step, we do our 3 equations. Okay? Summation of forces in x equals 0. Summation of forces in y equals 0. Summation of torques equals 0. Now, we start out with summation of forces in x. Are there any forces in the x direction? Do we even need that? No, we don't, right? But what about summation of forces in y? Absolutely, super important. So let's do that. Sum of forces in y equals 0. That's our first condition for stability, for static equilibrium. We know that the force of the bicep, right, is the only positive force. We have a minus force of the elbow, okay? We have a minus weight of the arm, and we have a minus weight of the book, all right? That's all the forces in the y direction. These are nice because we don't have to worry about r's or how far anything is away from the axes yet, right? This is just what's happening in y. Okay? That needs to be true in order for this arm not to levitate up into the air or fall into the earth. Those conditions need to be met. Pretty cool. Okay. What do we have and what we don't have? Well, we're trying to solve for these guys. We don't have this and we don't have this. But we do know that this is just 2.5 times 9.8. It'll be easy to calculate. And this is going to be 4 times 9.8. So that's easy to calculate. So far we have 2 unknowns and 1 equation. Big surprise where we're going to get the second relationship. We know that the sum of the torques must also equal 0. Okay? So, for starters, we have 4 forces. There should be 4 terms. But I'm going to tell you right now, because we picked this as our axis of rotation, and because the force of the elbow, right, the force on the elbow is acting on the elbow, R is 0 here, right? The force is acting at the same point as the axis of rotation, so that torque term goes away, and it makes this equation a little bit more simple because now we're only going to have 3 terms, okay? We're going to have the torque due to the bicep, so TB, right? And that's going to be a positive torque because if I'm pinning here and I'm applying a force this way, this arm's going to want to move counterclockwise. That'll be a positive torque. The rest of these will be negative because if I'm pinning here and I'm pushing a force down there, this guy's going to rotate down, which is clockwise. Okay? So minus the torque of the arm, right? And then lastly, minus the torque of the book. And that all has to equal 0. Well, what is the torque of the bicep? Well, the bicep force is, we don't know. We're trying to find it, right? So force of the bicep times that distance. Remember, it's 0.04, right? And then lastly, sine of theta, right? Torque is RF sine theta. And that angle is 90 degrees, right? So that's just 1. Makes life a little bit easy, right? Okay, what about for the arm? Again, sine of 90. That's 90 degrees, sine of 90. Minus, what's the distance? Well, 0.16 now, times the weight of the arm. Right? Which again is just 2.5 times 9.8. Super easy. Minus, how far out is this book being applied from the elbow? Well, that's going to be 0.38 times the weight of the book. And that all equals 0. Okay? Pretty cool. We can just go ahead and calculate those. In fact, I encourage you to go ahead and calculate them on your own. Right? Go ahead and find it. So weight of the arm is 2.5 times 9.8. Weight of the book is 4 times 9.8. Sub that in. We can easily then just solve for the force of the book. Or, yeah, of the bicep, right? This is the force of the bicep. So if I put in my weight of the arm and my weight of the book, the force that the bicep has to apply is, I get 470.4 newtons. Dang, pretty cool. Okay, I just found out what the bicep needs to apply to my arm in order to hold up that physics book. Okay, but are we done? No, we also need to find out what is the force that the elbow has to endure from, the force that's on that socket. Okay, which is basically a normal force, right? So what force must the elbow have to endure? Well, I can now just take this, put it right in here, right? Because I just found it. And then I know this. We calculated the weight of the arm. We calculated the weight of the book. And I solve this equation for Fe. When I do that, I find that I get an Fe, right, the force of the elbow, of 451.6 newtons. I encourage you to check me on that. Let me know if I'm wrong. But these are the forces that I am experiencing as a human being holding a physics book. Okay? For those of you who might want to be physical therapists, these are interesting questions, right? Because it tells you, like, what can we do? How can we configure this arm? What are the maximum weights of things that this guy could hold, okay, such that these are minimized, right? The whole goal is we want to minimize these forces, which are stresses on the elbow, stresses on the bicep muscle. How do we minimize that? And now we're beginning to see, by these kind of analyses, how we can go about minimizing different stresses on parts of the body. All right, we will continue with more examples in the next video.